Welcome to tutorial 16 on inverse functions. To start with, we need to define composition. That is, what happens when more than one function is put together. So if you have a domain x and a codomain y and the function between them, and a domain which also happens to be y and a codomain z, another function g, then the composed function is called g of f and goes from x to z. Indeed, g of f of x, an element of x, is equal to g of f of x. So as an example, suppose f goes from the natural numbers, so the positive whole numbers, to the real numbers, defined by it takes the square, and g goes from the real numbers to the interval -1 to 1, where g is the sine function. Then the composition, g of f of n, is equal to g of n squared is equal to sine of n squared. You should observe that g of f does indeed go from the natural numbers to the interval -1, 1. So what about the inverse? The inverse, if I draw a picture, is when you can go forward and back. Maybe this is f. So there's a unique choice to go backwards. So a function f is said to be invertible if there exists, that is, if you can find a function g going the other way, such that two things hold. So if I do g of f, so let's do f first then g, going from x to x, this is the do-nothing map on x. And secondly, going the other way, f of g, which goes from y to y, is the identity on y. If this g exists, it's written as f inverse, is the unique inverse function. So let me do an example. Suppose my function is from the real line to the real line. I'm just going to label them 1 and 2 to distinguish the domain and codomain. Then, if I define f of x is equal to just the +7 map, you can see that the graph of the function is this. There's f. And going backwards, what's this inverse? Different color. G goes from R2 to R1, and it takes, let's say that g of y, that equals y minus 7. So we can go two ways. We can take a point, so there's x naught, and it gets taken to x naught plus 7. But I could think of the inverse function as taking the point y naught and then subtracting 7. This is where we distinguished R1 and R2. If we always had the domain here, so if we just, as a separate example, if we just tried f maps R to R, and f of x is equal to x plus 7, some other function g mapping R to R, where g of x is equal to x minus 7, instead of this picture, we would get, well, f looks the same, but the inverse function would look like this. You see that these are symmetric around y equals x. It flips along y equals x. So you might want to try an exponential example. So say you have an exponential and its inverse would be a log. But let me do a different example for when a function isn't invertible. So that was example 1, this is example 2. And let's consider y equals x squared. So f maps the real numbers to, let's say, the positive or non-negative numbers, and it takes a number and gives you its square. You can see that this isn't invertible because if I just give you some value, I have a choice. Well, which value on x do I get to hit this value of y? So there's no unique inverse. But if you restrict, let's say that you restrict f to, well, we could either pick the negative reals or the positive reals. Let's pick the negative ones, why not? Or non-positive. So we only care about this piece. Then this piece is invertible. It's written f restricted to minus infinity to 0. And this has inverse. Well, pictorially, we know that it has to be reflection along the y equals x line. So it looks something like this. Let's draw that a bit better. It's the green one, which looks something like g of x is equal to minus square root of x, where g goes from the positive or non-negative reals to the non-positive reals.